as I said, today we're going to be talking all about these computer simulations and how they're really such a valuable tool for what we do in cosmology today. So looking back over the whole story of what these lectures are about, we've really been trying to explain how the universe was made. So a fraction of a second after the Big Bang, we had this period of inflation, which Austin spoke to you about. And then we had this moment where the cosmic microwave background was emitted. So this very early light, so basically the first light that's emitted that we have details of the Big Bang and what was going on at those very early times. And then there's a huge leap forward where we get basically the first stars turning on, right? So the very first light in the universe. And then with subsequent evolution and expansion of the universe, how we get galaxies forming and clustering, and how we get ultimately these beautiful structures that we see today of spiral galaxies and different types of structure within those galaxies. So what simulations try to do, what you would ideally want would be a simulation which follows all of this. Right? And at the moment we don't actually have that. We don't have a simulation which starts at t is equal to 0 and runs until today and is able to represent all of these things. So what simulations actually do are that they cover chunks of it. So you have some simulations which follow the formation of the first stars and how we think that happened. And then you have simulations which maybe follow the dark matter and what's going on in terms of the gravitational interaction with the dark matter components. And then other simulations follow the formation of individual galaxies. So actually trying to simulate this entire thing, because it's the whole universe, I hope you forgive us that we haven't gotten to that stage.
What about the Dark Age?
So the Dark Ages are before the first stars. So we definitely are not interested in that too much.
Well,
so at the moment it's challenging enough just to get the first stars right. Okay, so we have this picture of what the universe is made up of today. And the fact that this dark energy component, which we can think about as a negative energy in the universe, or we can think about it as an alternative gravitational force on large scales. Those two ways of thinking about it are equivalent. And because we don't know what dark energy is, we can think about it in either way. We have this other component of the universe, which is in this dark matter, which we definitely understand a little bit more about. We do think it is a particle, a dark matter particle, maybe one, maybe many. But it interacts gravitationally. It does not interact with light. And this component is one of the main particles, if you like, that are followed in these n-body simulations. So these large computer simulations. And then in simulations which focus on how the first stars formed or how galaxies formed, those simulations follow dark matter, but they also follow what's happening with familiar components of the universe, like hydrogen and helium. Neutrinos not so much, but it's become more popular recently to include neutrinos in these computer simulations. Okay, so what is our standard model of cosmology? So anyone who's used to particle physics would have heard about the successes of their standard model of cosmology, or sorry, their standard model of particle physics, where they recently found the Higgs boson. But our standard model of cosmology is called lambda CDM. So this term here, lambda, is referring to the dark energy component, and the CDM is the cold dark matter. So even though we have a name for our standard model, we really can't boast too much about it, considering we don't know what either of these two things are. So when it comes to comparing cosmology and particle physics, it's, they're definitely winning, I would think. Okay, so in terms of this dark matter component, which is what we really are trying to follow in these computer simulations, we had a whole lecture covering the evidence for dark matter and how we really think it is a particle that's out there. We understand its gravitational effects. And this is a really nice result, which was by R. Massey in 2007, where they used the Hubble Space Telescope and the effect of gravitational lensing, which is the bending of light by massive objects, in different redshift slices. So they basically mapped out the dark matter at different redshifts. So as you go back in time, these are represented by different redshifting of light. And by measuring the bending of light due to the dark matter being there, they were able to actually create a three-dimensional map of the dark matter from where we are today going back in time. And this made the cover of Nature here, where they went with the headline of the unseen universe. So this was actual detection of this unseen component, if you like, of the dark matter, which we're able to map out due to its gravitational effects on light. So one of the interesting things here is that this component of dark matter, seen here as these kind of blue clouds, that's not evenly distributed, right? It's not smooth. There's a clumping here. And you can almost make out some kind of filamentary structure, which we have other observations for as well. So when we run computer simulations, trying to get this type of structure where it clumps in a very particular way, that's ultimately the goal of people who run these n-body simulations. And if you understand the laws of gravity and how dark matter clumps over time, at the end of your simulation, you should end up with something that is accurate or is similar to the real world.
I'll do it for you.
So there's a few questions we're going to go over today, okay? So firstly, what are cosmological computer simulations? So many of you may not have even heard of these. Secondly, how do we create them, right? If you want to go home today and do it, you've got some interest in running these, you could, if you wanted to. The codes, some of the codes are public. The third question is probably the most important, is like, why are they important to cosmologists? Why are they such a useful tool? And then the fourth question is just out of interest, what are the biggest simulations ever run? So these are really cutting edge science on what are the largest supercomputers we're using to simulate the entire universe. Okay, so firstly, what are dark matter simulations? So as I mentioned at the beginning, you can get different components of the universe at different evolutionary stages that we're trying to approximate. And at the very basic level, if you're interested in the laws of gravity and structure formation without baryonic physics, we can just follow the dark matter only. So this is a computer simulation which was run in Stanford. Tom Abel's group there, just showing dark matter particle simulation. So you can just think about all these little blobs here as being gravitationally bound groups of the dark matter. And as you can see, it's not homogeneously distributed. So there is structure there which tells us a lot of physics. One of the other interesting things that we need to think about when we run these computer simulations is the scales on which they are accurate. So if we are trying to represent something which is where a galaxy will eventually form, then we're interested in these dark matter halos. So these are large gravitationally bound structures, and we need to be aware of, well, what scale is our simulation accurate? Okay, because we can't go down to infinitesimally small scales. There is what's called a resolution limit to our simulations, where beyond that we know that the simulation is not accurate. So when you talk about these simulations, people refer to, well, I'm able to resolve the halos where something like a Milky Way galaxy would form. Other simulations are not able to resolve those halos, and they look at much bigger structures, maybe clusters of galaxies or things like this. There's other simulations which go even further and are able to resolve the halos which are of a lower mass and represent where dwarf galaxies would form and things like this. So this is showing a slice from an n-body simulation where basically we are zooming in on one of these dark matter halos, one of these bright nodules here, which represents an overdense region where matter has fallen in due to gravitational attraction. And then we can zoom in more and more and more until we eventually get down to this scale, which is the individual dark matter halo where a galaxy will form. So other people try to simulate just one galaxy, for example. So this is a huge challenge in itself. So in order to simulate galaxy formation, we also need to understand a lot of baryonic physics. So what's going on in terms of the temperature, the pressure, the density of the gas, and how those are all interacting. So in this simulation, you're not just seeing the effects of dark matter. This is inside a dark matter halo now, and now you're actually looking at the gas. You're looking at hydrogen and helium, and you're also seeing the formation of a spiral galaxy. So you can see how the material is being accreted in. The angular momentum of the galaxy is causing these particles to fall in and fall out. So you have several crossings as the material flows in. And eventually you can recognize this, even though this is a computer simulation. It's following all the physics that we think go into making up those beautiful spiral galaxies that we might have seen from the Hubble Space Telescope images.
What's the time scale?
These are billions of years. So yeah, even though, 2 minutes, it's, billions of years. So these simulations are really challenging, and this is still cutting-edge physics, trying to understand how these form, to get the details right of how many stars are in these galaxies. Okay? What's happening with the central black hole. We think the black holes are really very, very important to the formation of these galaxies. How the black hole interacts with the rest of the material in the galaxy, this term called feedback. How the black hole is actually ejecting material from the space around it and sending back and enriching the gas around the actual central galaxy. And you end up with something called a central bar here in the middle. We're viewing this face on. If we viewed it edge on, you would see this material being expelled out and then falling back in due to gravity. So trying to get this right, trying to get the statistics right, the numbers of stars of a certain type that you form, all of those are details, which is really cutting-edge science. So we're not just trying to make pretty pictures. One of the things people are also interested in are these very first stars. So what happened, after the Dark Ages. So this simulation is showing the formation of one of those first stars. So they were very massive, intensely bright, and they emitted a lot of ionizing radiation. So this is showing one of these first stars turning on, and then you'll see a blue envelope forming and moving out from the central first star. That is ionizing radiation. So very, very fast photons or particles of light with lots of energy, which interact with all the gas around it and ionize. We call this the reionization of the universe. So these first stars, which formed in dense clumps of gas and dust. And we see scenarios like this, the birth of new stars in places like nebula in the universe. So if anyone's seen these beautiful pictures of the Orion Nebula, you will see these stars turning on inside their dust clouds.
Can you go back? I didn't see all of the text on that.
Oh, sure. Yeah. Let me see if I can close it.
Yeah.
So we call these first galaxies proto-galaxies. So we think that these stars formed after, say, the first billion years. And the interesting thing is that you can see that the ionizing radiation actually blows apart the gas and the dust which are surrounding these first stars. And this is a very important process, this reionization of the universe.
So it leaves the atoms with missing electrons?
Exactly, yeah. So it's this reionization which is very important. Yeah. Okay?
Thank you.
Yeah. Okay. So that's what they are and all the different kind of flavors that they can come in. And the second question is, well, how do we create them in the first place? And I'm only going to talk about the dark matter simulations just because those are kind of the easiest to get to grips with. If you wanted to talk about the simulations of the first stars and how the gas is forming and stars are forming in galaxies, then the physics of that is a lot more involved. But if you're interested in that, please ask me afterwards. Okay, so M-body simulations in a nutshell. So this is basically what we are doing. In the computer, we take a box, it's a cubic box, and basically what we have are particles, and we follow the gravitational interaction of those over time. So we have some physics, some mathematical equations for how we think two particles interact given a certain distance and given the mass of the particles. And then we basically just follow these over time from an initial condition which we set up in the simulation. We evolve this over time at discrete time steps. And then we follow how the particles clump and move and react to one another within the simulation box. And at the end, over many, many, many time steps, we want to end up with something at the end that looks like the real universe. Okay, so that really is it in a nutshell. The only trouble is we're not dealing with a handful of particles when we run these simulations. We're dealing with billions or trillions of particles. So the real issue is when you're calculating these equations, although they look incredibly simple, in order to do it in a time which is available to someone doing a PhD or a postdoc, what you really want to do is have some computational method for quickly evaluating the force law of billions and trillions of particles at each time step from very early universe until today. Okay, so these simulations the largest simulations take months to run. And basically what they're doing is updating these force calculations using clever methods at each time step and making sure that you're accurately representing the force of gravity in the simulation. So these are for this n body, n representing the number of particles. So these are the dark matter only simulations. So where do we generate these predictions? So as you can imagine, these large computer simulations are international collaborations between lots of different universities and research centers. And so these simulations are run on the largest supercomputers in the world. So this is one example here. This is our closest supercomputer. It sits at Argonne National Laboratory, which is very close to Chicago, and it's called Mira. This is the third fastest supercomputer in the world. As you can imagine, America, I think, is still leading. There's a kind of a competition at the moment who is the fastest supercomputer, but I think America is still up there. There's a supercomputer called Titan at Los Alamos, which also runs computer simulations. So these are not exclusively for the use of cosmology. You also have people who work in biology, DNA sequencing, particle physics people running on these computers. So in a sense, you share time on these computers. One of the big challenges in building bigger and bigger computers that can perform faster and faster calculations is keeping down the heat of these machines. That is the real challenge here. These machines generate a huge amount of heat, just lost energy, due to what's going on the microprocessors. One of the interesting things at Mira is that they've designed, I think you can see them in the back here, these copper pipes which actually flow over the chips, and they contain cold water to cool down the individual chips. If you ever get a chance to go in and see a supercomputer, I really recommend it. They're amazing. One of the things that's astounding is the noise of these things. You cannot hear people talking, the amount of noise that these generate. So the number of computers that's in Mira, this is 500,000 processors, or 500,000 CPUs in the Mira supercomputer. So I'll show you simulations later which were generated on this machine. Okay, so as I mentioned, how do we do this? So we start off with our box. This is at very early times, very early redshifts. And we have some notion of what the initial conditions, so what the early universe looked like. So we think it was very smoothly distributed materials. This is a dark matter only simulation. So before the effects of gravity have really kicked in, we think it was fairly evenly distributed. This is coming from the cosmic microwave background. But there were small fluctuations in this distribution of matter. And those small fluctuations are incredibly important because they are the things that seed structure formation in the late universe. So as you run your simulation forward in time, you can see structures start to appear in very specific areas. And then as you zoom in, you can see today, 13.7 gigayears, that we have some filamentary structure. Okay, so this is not evenly distributed. There are clumps of dark matter, and these are the sites where galaxies will eventually form.
The first one showed this kind of lines horizontally. That represents some kind of what we call it the sound that it was found.
Which one?
The first one, see, on
This
the bottom there, they have these creases
Yes,
that go horizontally.
So that could just be effect of how you've actually made this picture. It could just be a bad pixelation of the picture. But yeah, ultimately these are just discrete particles. How you're doing this, right? So there is going to be, in a sense, a resolution limit. If you keep zooming in here, it's going to look very pixelated.
Is there any reason why you wouldn't just take the same formula and start with the current situation and run it backwards and see what you get?
That's religion.
So unraveling, I mean, so why would you do that?
To see what it started as.
But these are completely deterministic, right? There's no stochasticity in there. I mean, if it works one way, it should work the other, right? But in terms of setting up these initial conditions, this is easy to do. Setting up this is not easy to do. Okay, just computation. It's very good. So maybe if we leave all the questions to the end, that's cool, and I can just keep going. But there'll be plenty of time at the end for lots of questions. So we do have a very good understanding of what these initial conditions should be, very tight constraints on these. And this is why we run the simulations forward in time. Setting up these is easy computationally, but also we have very good evidence for what those initial conditions should be. And that evidence for what the initial conditions should be comes from this, the cosmic microwave background. So this is the very first light in the universe emitted after photons, so light particles, decoupled from that plasma that was emitted or created at the end of inflation after the Big Bang. So what you're looking at here are temperature differences in the light that is coming to us from that very, very early time. And this is telling us about the universe at that very early time. So if you remember back to the lecture where I spoke a lot about the cosmic microwave background, we have this evidence that it's incredibly uniform. That all these parts are very similar. Parts of the universe which are actually what we call causally disconnected look very, very similar. And then we have these very small perturbations. So if you remember, these perturbations are at the level of 10 to the minus 5. That is the level, the very, very small temperature differences that you're getting. Right. So the very first measurements of the cosmic microwave background found just a uniform temperature, right, of about 3 Kelvin. And we really have to go to very, very small differences in order to see these quantum fluctuations. So these small differences are telling us about interactions that were happening in the very early universe. So when you have the photons coupled with the quarks in this kind of soup in the very early universe, they're interacting via two effects. So you can boil it down to a push and pull between the gravity of the dark matter and then a photon and an electron pressure which are resisting that. And you get these oscillations in the fluid. So we spoke about this before. And this gives rise to these temperature differences, which you can see plotted here as a function of scale. And then this red bar is just showing, as you move along in scale, what these temperature fluctuations look like. So hot and cold spots in the radiation. And ultimately, these hot and cold spots in the radiation are also imprinted in the matter distribution. So we take this information, which we understand very, very well and has been measured to exquisite precision, and this gives us our initial conditions for how to distribute the matter in the n-body simulations. So this is why we have a very good understanding of the initial conditions in the universe, that the dark matter was evenly distributed with very, very tiny fluctuations, so very small overdensities and very small underdensities. And they're not just randomly distributed either. Okay? So where do these fluctuations come from? That's still an area of study. So we think they came from quantum perturbations from the decay of the inflaton. But you can think about it as this is really still cutting edge research. How do we generate these perturbations? We're able to measure them. We're able to predict how the radiation, the signature of these fluctuations is imprinted in the dark matter. But actually how they're generated in the early universe is still not very well understood. So if we take this simulation then and we have this evenly distributed amount of material in the dark matter, now we're just following the dark matter only, and we run the clock forward in time, we get to see this clumping of material. So the color coding here is yellow for more overdense regions and a lighter blue for underdense regions. So very, very particular regions where the dark matter falls in and aggregates. But there's some very interesting structure here, okay? It's not just uniformly distributed. And you can really see these filaments which connect the overdense voids, or sorry, the overdense halos. And then you also have these very sparse, underpopulated areas, which we call voids in the universe. So this is in the dark matter, but we believe that the galaxies are forming in these locations, okay, in the dark matter halos. So in a sense, the galaxies should also follow this distribution of being aligned along filaments and then ultimately aggregating inside overdense halos. So one of the interesting things is what's happened in terms of the evolution in the codes themselves. So when these simulations started, the very earliest simulations were back in the 1960s, and they were following 16 particles. So not very robust calculations, as you can imagine. I think then in the 1970s they got up to 100 particles. And today we're up to trillions of particles. So this evolution in the code was actually following what was happening with the evolution in computers themselves. But how we calculate the forces and how we do this rapidly at each time step calls for more and more levels of sophistication in the codes themselves. So very early codes were basically just putting down grids where the individual particles were smoothly distributed over the grid, and the forces were then calculated at each time step on this grid. Then the next step up in terms of the codes was what was called adaptive mesh refinement. So this is where you can refine your grid, make the grid sizes smaller and smaller in the areas of interest. Right? So if you have an overdense region, we really need to zoom in there. We need a better resolution in those overdense regions. A better resolution represents smaller pixel sizes or smaller grid sizes. But we don't want to waste too much computational time in these underdense or void regions because there's not many particles there, there's not much going on, and we don't want to waste computational time. So you can really speed up your simulation by using this adaptive mesh. Okay? And at each time step, the code itself knows when to adaptively refine. So that's a very interesting adaptation. And then the next stage is this tessellation method, where you have irregular cell sizes in order to follow the particles. And this is interesting from another point of view in terms of accurately assigning volumes to each of these particles to follow them over time. So this grid can be seen as a little bit artificial. So you're restricting particles within the grids, or you're restricting your force calculation within the grids. Whereas when you tessellate, obviously mathematically this is a bit more involved, but it's more rigorous. You're able to define the force calculations and the density more rigorously when you use these tessellation methods. So these are very interesting. So this is actually a simulation code showing now the state of the art in what these codes are doing. And this is a moving mesh code. So the mesh now actually deforms with the density of the fluids. And this is showing, I think it's a Rayleigh-Taylor instability. This occurs when you have two fluids of different viscosities which have different velocities. And basically you get those very, very beautiful tails that are shown. But you can actually see in this simulation the moving mesh cells. And the reason that this is important, or the reason that it gives you an advantage, is that you're accurately following the changes in the density at the interface between the two medium here in a more, let's say, flexible way than a fixed grid would do. So how are these things, how are they important? So these instabilities, I'll just show this again, these actually occur. You can go online and look at these patterns. You see them in cloud formation sometimes. Okay, so this actual following of the velocity differences in the viscosities in fluids, these are applicable to phenomena that we see in the real world. And when you do simulations of galaxy formation, all these interactions between the viscosity, velocity, and densities of the fluids are very important when you're trying to form things like galaxies and stars. So this moving mesh code is very, very cool. Okay, so that's how we create the computer simulations. And why are they important? So this is probably the most important question that we want to ask. So one of the things that M-body simulations have really revealed to us is this notion of a cosmic web. So this is a really nice poster from a meeting that we had last year, last June in Chicago. And what they've done is they've taken a computer M-body simulation and imposed it on the sky, but you can also see the reflection there in the beam in CloudGate. So I like this poster a lot, but one of the interesting things is that before we had computer M-body simulations, we were not aware of this web-like structure. So this is called the cosmic web. And the elements of the cosmic web are what I've spoken about before. So these dark matter halos or nodes, which are the overdense regions, these filamentary structures, and then the underdense regions here, the voids, where there's not much going on, where we may have galaxies. So the actual interaction between these three components, how the three components form, this is what's important, and these are why M-body simulations tell us a lot about the interactions in the dark matter and ultimately how galaxies form within this cosmic web. So the simulations allow us to follow this over time, and what we're really seeing here is, if we're analyzing, well, we want to figure out how this dark matter halo is forming, right? Because ultimately this is a gravitational potential well. All of the matter is being attracted due to gravity. And then how is the gravitational potential well, how is this halo being fed, in a sense? And these filaments are the key to how material flows into the gravitational potential well. So you can think about these filaments as expressways that drive all the traffic into an overdense region, and ultimately those overdensities will be the places where the galaxies form. So these filaments are very, very important for how the gas flows into a dark matter halo and eventually cools down at the center of the halo and then starts to form stars and galaxies and things like that. Then how the filaments are distributed within underdense regions is also a very interesting area of study. Okay? So these overdense regions where we are able to see galaxies moving away from an underdense region and they're being propelled towards overdensities. But then these filamentary structures, the notion of, well, are they dense enough to form galaxies? How are they distributed within the voids? All of these things we're able to analyze statistically and then compare with observations. So M-body simulations have really been key in building up our idea of how galaxies form and interact with dark matter. And today we have this notion of a hierarchical galaxy formation. So this notion that in the beginning, small things formed first and clumped together under gravity, and eventually formed groups of galaxies or clusters of galaxies. So here in this picture, in this cartoon, you have the gray representing the dark matter halo, and in the very beginning we can say, okay, well, what if each galaxy sat in its own dark matter halo, and then over time, maybe the halo merged and you end up with more than one galaxy in a dark matter halo, and then you end up with some distribution of galaxies. Maybe you have a central galaxy, or the brightest galaxy in a cluster, and then you have some satellite galaxies. So this is our notion of how galaxies actually form today and clumped, how they are distributed in the universe. So it didn't have to have been this picture. In the beginning, people thought, well, what if it was the opposite way around? What if we started out with these large structures, which were all connected, and then everything fragmented? So that was another idea when people first started studying galaxy formation. And that scenario was called the top-down scenario. So you start with the very large structures all connected and then everything fragments. Whereas this scenario is called bottom-up. You create things small first and then work your way up. But it was ultimately using M-body simulations of those two scenarios. We were able to create M-body simulations which did this top-down approach and then compare with the real universe. And it was only by comparing with the real universe that we were able to focus in on this one method for forming galaxies. So this is why nobody talks about the top-down evolution nowadays, because it does not fit with observations. So you can really think about the dark matter as kind of a cosmic scaffolding where galaxies are built. And this simulation is by Orsi et al. In 2012. They ran the simulation in Durham in the UK. And in green here is the dark matter distribution. And then these bright white dots are where you would expect the galaxies to form. And then, of course, there are different types of galaxies here. So this is representing a different type of galaxy that you would have forming in this simulation at a very high redshift. So the connection is what we observe in the universe are galaxies. We don't directly observe the dark matter. So when we're trying to compare the predictions from an M-body simulation, what we need to understand are where the galaxies sit in the simulation, okay, how they're statistically distributed, and then how ultimately these overdense regions in the dark matter are formed. So this is the connection with, if we think we understand the laws of gravity, how the dark matter clumps together and forms, and then we think we understand how galaxies form within the dark matter halos, we can then populate these dark matter halos with galaxies and produce predictions for what the galaxy surveys in the real universe should see. And this is what people have done. Okay? So this is actually showing the comparison between computer simulations, right, shown in red here, the two wedges in red, and this is real data here from the real universe. So this is from the 2DF Galaxy Redshift Survey, this slice here. This is showing the distribution of galaxies within a wedge because we're at the center looking out. And as we go back in redshift, looking back in time, we can start to see hints of this cosmic web. Okay? The galaxies are not smoothly distributed. They have this clumping nature, there are underdensities, and filamentary structures as well. And then you can compare it with an M-body simulation, and you can see that it looks very, very similar. But you'd be hard pushed to tell which are the observations and which are the computer simulations. And then we can focus in, so this is from the CFA survey, showing a galaxy cluster. So this is the famous stick man of the CFA survey, because if you can look close enough, you see a little man here. I don't think that has any cosmological significance, but it's kind of interesting that you can get these large clusters, so the sizes of these things, and how they're connected by filaments. We also see this in n-body simulations. They don't look exactly the same. We're not trying to reproduce the universe exactly. We're trying to reproduce it statistically, so this is a realization. So we're trying to say, on average, do we get things of this size? Do we get the same numbers of things on average? Okay. So we can really think about what computational cosmologists are doing as cosmic cookery. They have a certain set of ingredients for how to make a galaxy, and then we put all those mathematical ingredients into the computer, we run it forward in time, and we compare with real observations. So one of the key things that we need, if we want to represent the real universe, we want to get dark matter to clump in a certain way. Okay? We want to end up with halos of a certain size, dark matter halos of a certain size and of a certain number, that will correspond to the birthplaces of galaxies. So if we don't know the exact properties of dark matter, we can use these computer simulations to speculate. We can say, well, what if dark matter interacts like this? What if dark matter is not just one particle, what if it's two? What if there are some unusual properties to the dark matter? So this is an example of this, where these computer simulations are really great fun. Okay, you get to play with physics, and then you get to see what you get at the end. And this is 3 simulations showing you different velocities for the dark matter particle. So when we talk about cold dark matter, this cold refers to the velocity dispersion of the particle, so very small velocities on average. And we end up with a universe that looks like this in the computer simulation. So again, you have the filaments and the voids and the overdense halo regions. And if we zoom in on one halo in particular, we can see a central overdense region with lots of little substructure around it. So lots of yellow overdensities. So the central area here would represent where the main, the largest or brightest galaxy would sit here at the center. And then you may also have satellite galaxies in this cluster, which would sit in these smaller overdense areas. But what if dark matter had a higher temperature? Okay, what if we heat it up a little bit and it's a warm dark matter component? Now the dark matter has more velocity. Or you can even turn up the temperature a little bit more, give the dark matter particles even more velocity. And now what you see in the computer simulation is that you've completely erased the structure of the particle. Okay? Now the velocity is fighting against the gravitational attraction, and you can see you end up with a lot less structure compared to a cold dark matter component, and you end up with basically a washed out distribution of the dark matter. And then this is going to have huge implications for the distribution of galaxies ultimately. Okay? In this picture, when you zoom in on a halo, you have a central halo, but you have far less satellite galaxies. And this is something which we could compare with predictions. So if we look a little bit closer to home, so in our galaxy, the Milky Way, we have several satellite galaxies which belong to our local group. And 2 of our satellite galaxies, which are the only 2 visible from the southern hemisphere, they're the only 2 visible in the night sky, are the Magellanic Clouds. So here they are here. These are our neighboring galaxies, the large and small Magellanic Clouds. And we have others, but these are the only 2 which are visible from the night sky. But if we were able to turn on our dark matter vision, what we would see are dark matter clumping around these 2. Okay, and a very particular mass of dark matter which clumps around these 2. So not only are we sitting in one common halo together, but there is also a distribution, a clumping of dark matter around these 2, and this must have been there for these 2 satellite galaxies to have formed. So if we look at the observations, here we have in gray what we think is our dark matter halo. The Milky Way galaxy sits at the center, and we have something close to 20 satellite galaxies which we've observed in our local group. So now you can say, well, this is the real world, right? This is the real observations. What do the computer simulations say about this? What are the predictions for the number of satellite galaxies that should be around a galaxy like the Milky Way, if all of our calculations are correct? So one of the key issues at the moment that people are still researching is that in M-body simulations, so this is an output from an M-body simulation of a halo which we think would harbor something like the Milky Way, you can see you end up with lots more substructure than we actually see. So this is called the missing satellite problem. It's still an area of research. And if we go back to the 2 previous slides, you can see that perhaps if we turned up the velocity, if we turned up the temperature of dark matter, we can erase this substructure. So this has prompted people to research more into maybe a warm dark matter component, where we erase the substructure in order to compare and ultimately get out accurate predictions for the real world. So this missing satellite problem is still ongoing. We produce way too much substructure. All of these little dots here should be satellite galaxies, right? And we don't see hundreds of satellite galaxies around the Milky Way. So that's one example of how M-body simulations can really tell us something about how the dark matter is distributed. The second interesting thing that you can use M-body simulations to do is that we know that the dark matter interacts through gravity. And we have this perplexing 70% of the universe which represents a dark energy component, right? So you can say, well, what about our theory of gravity? Can we use these simulations to run mock universes where maybe the theory of gravity has changed a little bit? So we have this notion of the interplay between what the dark energy is doing, so this unknown component of the universe which has started affecting the expansion, basically accelerating the expansion relatively recently. So this dark energy represents something that is pulling galaxies further away from one another. And then you have the dark matter, or this large gravitational component, which wants things to clump together, so be attractive under gravity. So we can consider this a cosmic tug of war. So when we think about how structure forms from very early times until the present, if you're trying to form galaxies, then the interaction between dark energy, which is a negative gravitational force, and dark matter, which wants to clump together, the interplay between those two needs to be just right so that we get an observed universe, or we get a predicted universe that looks like our observed universe. So I mentioned 2 weeks ago how annoying it is that GR has been proved right in so many different arenas. Okay? So if you're trying to modify gravity in order to explain dark energy, it's very, very hard to do that. And ultimately, we need any modified gravity theory to look like GR, to look like general relativity in lots of different environments. So we have all these different evidence that GR is right, but ultimately we have this component dark energy which we don't understand and may be due to modifications to gravity on large scales. So this notion that any change which you make to gravity has got to be very, very small, okay? Because you don't want to disrupt all these measurements of GR. These are exquisitely precise measurements. So when we run simulations with modified gravity, in a sense, you can imagine the differences are not going to be that large. So this is showing you output from 3 simulations and 3 different panels. And you'd be forgiven for thinking that they're all exactly the same. Okay, but they're actually, 2 of them have different gravity to our standard model. Our standard model for GR is sitting here in the middle, where dark energy is represented by a cosmological constant. So this energy of space-time is what's causing the accelerated expansion. And in this middle panel, in these other 2 panels, we've changed gravity slightly. So we've altered the force between the particles. And they do look very, very similar. But if you focus in, you can really maybe see, if your eyes are good enough, you can see very, very small differences. So maybe the voids look larger here. This area here, this dark matter halo, looks slightly more overdense than this one. So just visually, it's very, very difficult to tell the difference between these modified gravity theories. So it's really statistically. We have to go and look at the statistics. Or we have to zoom in. And if you zoom in, and maybe if you look at higher redshifts, you can see some of the differences. So it's not, you can see here that there's a lot more structure here, maybe in the void region than here. So in this modified gravity model, we've actually increased the repulsive force of gravity. So as we would have expected, the voids are more evacuated, more empty in this formation of the halo than in the standard model. So these very, very small differences, ultimately we have to analyze those statistically and produce predictions. So this is showing you what we're faced with here. If we want to just go into those simulations and count the number of objects, okay, that's something we can compare with observations. The number of galaxies, the number of dark matter halos that we get as a function of the mass of the halos. Then we're talking about very small differences in the number of halos once we try to modify gravity. So these are our predictions from the simulations. Then we're hoping that astronomers come along and make measurements of the number of objects of a certain size to the level of precision that we need in order to rule out these modified gravity models. So at the moment we're not quite there yet. Some of these small changes are still allowed. So if you're still doing research in modified gravity models, you still have a job for the next while. Okay, so on to the last bit, which is what are the biggest simulations ever run? So this is kind of the first grand challenge run that was ever done, and this is called the Millennium Simulation. It was run in 2005 by Volker Sprengel. He was a grad student at the time working in the Max Planck in Munich. And this was an impressive thing to do for your PhD project. So here you can see, I think it was, this is just a small part of the simulation, but this was 10 billion particles took part in this simulation, and it took months to run on a European supercomputer at the time. So that's the Millennium Simulation. This was also made the cover of Nature magazine, which was quite rare at the time because Nature normally publishes observations from the real world. So this was breaking from their tradition, publishing a result which was just a numerical simulation. We also have another grand challenge, which is the MICE universe. This is a group working in Barcelona in Spain. And they have upped it to 70 billion particles. So as we go forward in time, people are simulating more and more of these particles, and they're able to represent more and more of the universe. So as our cosmological surveys, as our galaxy surveys get bigger and bigger, we need the simulations to get bigger and bigger in order to produce predictions for the surveys. The interesting thing about this MICE collaboration is that the supercomputer that they ran on is called the Mare Nostrum. This is a picture of it here. It actually sits in a deconsecrated church in Barcelona. This is a picture of it. It's quite a dramatic setting.
That's the only big spaces they have in space.
Yeah. So maybe this is good luck for the predictions of this. So this, sorry, there's some text missing up here. So this is another grand challenge, which is the same group as the Millennium Simulation. This is the follow-up called the MXXL, or Millennium XXL. This is basically 8 times the size of the Millennium Simulation. This is 300 billion particles now. This was run 2 years ago. And this is showing one slice on the background here, and we're zooming in further and further until we get down to a dark matter halo. So in this simulation, we're able to resolve halos which should harbor something like the Milky Way. But we're also able to make predictions for much larger structures, like the bullet cluster, things like that, which are not just individual galaxies, but whole clusters of galaxies. So getting this range of scales and making sure that your simulation has accurately followed the gravitational interaction, that is really the challenge that people are trying to answer with these very, very large simulations. There's another group in France, so everyone's trying to trump each other. Okay, this is what's going on at the moment. And in the papers that are being published, it's very common for you to show how big your simulation is compared to other things. So this is the JUICE FIR simulation, which came out last year. They now have 550 billion particles compared to the MXXL, which people were boasting about 2 years ago, but now they've been humbled by the size of this large simulation. But you can take solace in the fact that Americans are still leading the way. So this should read up here, sorry, the MIRA universe. So this is a simulation which is still currently running on the MIRA supercomputer in Argonne National Laboratory. The computational cosmology group there, I heard a talk from them yesterday. They were saying that this simulation is at redshift of 0.4, so it's quite close to finishing. Because they share the supercomputer with other research groups at Argonne, they have to turn off the simulation and then turn it back on when they get free time, because this simulation takes up the entire 500,000 computers. So this really is an incredibly impressive simulation, and this is 1.1 trillion particles are being followed. Okay, so that's really all I wanted to say about computer simulations. So next week will be our last lecture in the series, and then I'm gonna try and show you what we're going after in terms of dark energy. What are the signatures of dark energy that people are trying to hunt down in future surveys? Thank you. So if anyone has any questions, I'll take them now. Yeah, back. Yeah, so the dark matter is also produced from, so after the Big Bang, we have this notion of an inflation, or a field that causes a rapid expansion. The decay of that particle which causes the inflation, or the decay of the inflaton, this generates these particles that we see today. And it generates all, in our current theory, this is what generates all the particles, the baryons, the electrons that go around the quarks, and the dark matter.
When you say generates, you mean
So,
density of matter and
so when I say generates, I mean that you can think about particles as being electric or energy fluctuations. Okay, so when we think about quantum field theory, what particle physics has told us is that we really can't think about fundamental particles as being energy fluctuations, which are localized. So when I talk about particles in the early universe, I'm talking about, you can think about it as terms of energy perturbations. But how they are produced, how the inflaton decays and gives rise to all these particles, that's still an area of research, because we don't understand what the inflaton itself was doing at that very, very early time. Yeah, question 5.
When the initial conditions for the simulations, do they randomize the starting masses of particles?
Yeah, that's a really good question, yeah.
Does baryonic matter make any difference in simulation?
So it depends. There's different types of simulations. You can run simulations without baryonic matter, just dark matter only. And yes, so in the beginning, what we're doing is we're generating one realization of the universe. Okay? So you don't just run one simulation, because ultimately you don't just use the pictures, you use the statistics from the simulations. So you generate lots of these simulations. So recently there was a group in Japan which generated 5,000 simulations. And they were exactly the same simulation with different initial conditions, so different fluctuations. So because we think that in the early universe you have this distribution of smooth material with very small perturbations, how those perturbations are distributed, we have some probability for that, right? So you want to do realizations, different realizations of the universe, and then take averages, and then compare with the real world. Yeah.
When you're predicting or simulating the location of a possible galaxy, do you have as one parameter the rotational force of a potential galaxy, or does that really mean anything?
No, so the angular momentum is something that's followed in the simulations as well for individual galaxies, sure. Yeah, so that's definitely followed, and also for each of the components, how each of the components are interacting, that's followed over time. Yeah.
Why weren't computer simulations in the 1960s capable of predicting inflation, and computer simulations in the 1990s, why did they fail to predict the increasing expansion of the universe? What are the limitations of computer simulations that resulted in their failure to predict what physical observations did?
So I don't think so. Computer simulations never predicted inflation. Right? I think all of those predictions of the expanding universe, inflation, dark energy, they all came from observations. So in a sense, the simulations are responding to observations rather than the other way around. So my example in the talk was of these satellite galaxies. We have observations telling us that there should be at most 20 satellite galaxies to our own Milky Way. And then simulators go off and they run the simulations with the physics that we think go into forming galaxies and dark matter halos, and then we compare with the observations, and then we go back to the drawing board if we're wrong. So it's more that observations are teaching the simulators rather than the other way around. Although when we do that, it's not just a one-way path, right? We take that observational evidence, we run our simulation, and then we do generate new predictions. So we say, well, maybe if you look for galaxies of a heavier mass in this region, if our theory is correct, then you should find this number of satellites in that environment. So it's definitely two-way communication in terms of the two areas, observations and simulations.
Thank you.
Yeah, very good.
Observationally, in the 1980s, they discovered the great attractor, which tended to display galaxies up to about 11 megaparsecs, moving towards the great attractor. Does that have an effect? Would that be a major trump?
So that's very interesting. And doing a simulation which reproduces those large-scale bulk flows that you talked about of the great attractor. So these are very high velocities, very large-scale effects where you're seeing a bulk flow along filaments to an overdense region. Ultimately, those are exactly the things which we're trying to answer in these simulations. If you run a simulation with your theory, your favorite theory for what gravity is doing, you want to make sure that you get high-velocity structures or high-velocity movement of material that we see in the real world. So the great attractor is a great example of that. These large-scale bulk flows are a very, very interesting area of study. And ultimately, when we have this notion of the cosmic web with filaments and how material is flowing into and along those filaments, really the crosstalk between observations and what the simulations are telling us is very, very important. Yeah.
So I assume that in these simulations, the part of the reason you need such massive computers is because you're trying to compute the effect of every one of these trillion particles gravitationally on every other one.
Yeah.
Consistent with the idea that the range of gravity is infinite, and however small it might be, it never goes to zero with distance. Yet you use the term gravitationally bound. I wonder if you could define that and its significance for this kind of picture.
So it's a relative effect of forces. Okay, so it's the same notion that you have, even though gravitationally the range of gravitational interaction is infinite, if you're close to a massive body, then you're going to be gravitationally more impacted by that massive body than some neutrino on the other edge of the solar system.
Is there some rule of thumb, dividing line, where you can say it's close enough to be gravitationally bound? And
yeah,
or is this
definitely. So this notion of the range of scales and what's important in terms of your local environment is how we say that these galaxies are bound. As a rule of thumb, you have to go to the equations. It depends on the mass that you're close to and the distance from that mass, and that's basically what's in it. If you're talking about Newtonian gravity, or you're talking about general relativity, it's different because then you need to take into account the actual curvature of the space-time. So I can't just give you one number and say, well, that's where we can say we don't care about anything else outside. Okay? Yeah.
And any of these simulations we each are, does any of them show a black hole?
So I didn't show any simulations of black hole formation, but people do those as well. And those would be not in the cosmological simulation. So when I say cosmological simulation, I'm referring to where we're trying to simulate the whole universe or the observable universe. They're in the smaller simulations where people just look at one galaxy. Because actually following the physics of what's going on with the central black hole and its interaction with the material and the dust and the gas and how that black hole is accreting material is very, very complicated. So we cannot at the moment run simulations which follow all the evolution of the dark matter as well as the evolution of a single galaxy with a black hole in the center. But yeah, people do run simulations of black hole evolution, rotation, and the effect of the black hole on the galaxy. And black holes are actually very, very important in the formation of our galaxies and making sure that we have the right amount of stars. Okay, so if you take a certain amount of gas and dust and you let it fall into a dark matter potential well, and if you don't have any black hole at the center, right? If you don't have any black hole feedback, any communication between the black hole and the central galaxy, you actually end up with too many stars. So this was a key input into galaxy formation a few years ago when people realized that without black holes, your simulations predict far too many stars compared to the real world. Yeah.
Virtual particles are produced through fluctuations from background energy of the universe. It's thought we also talk about the fluctuations in the early universe producing the distribution of dark matter. Were the fluctuations in the earliest universe such that they always produced particles, which
Stable
then
particles.
they always produced particles? There weren't fluctuations that did not produce particles.
So these fluctuations are stable particles. We say that they're on shell quantum mechanically, so they persist. They're fluctuations that persist, just like particles that make up everything that we see around us are stable fluctuations that exist.
So could you say then that the distribution of dark matter is basically due to the attraction of these particles to one another?
Sure, yeah, exactly. Yeah.
Does the simulation that you show that dark matter is cold, and that jives with the idea that dark matter doesn't interact with electromagnetic light and so on? Will that be against the concept of being cold? Because how does it get cold if it couldn't emit the radiation to cool off?
So you can lose energy through your gravitational interaction with particles.
Through what?
You can lose energy in other ways, as you don't have to emit radiation to lose energy. So these dark matter particles, in all three scenarios that I showed, in warm, hot, and cold dark matter, all three of those are still a dark matter particle in terms of not having an electromagnetic interaction. For the middle panel, the warm dark matter component, a candidate for that would be neutrinos. So let me see. The middle panel here, this warm dark matter, if neutrinos, we know neutrinos make up some of the dark matter. Okay, they can't make up all of it. But if a neutrino does not interact electromagnetically, it interacts via the weak force, a different force. So if the neutrinos were all of the dark matter, then they would look like the middle panel. Okay? So you can have other types of interactions depending on what is the candidate you're putting forward for dark matter. Okay, and maybe one last question, yeah?
Yeah. When you say cold, warm, and dark,
Yeah.
what order of magnitude are you talking about? What is warm and hot?
So velocity dispersions for hot, close to the speed of light, but not at the speed of light. Cold dark matter, we're talking on average hundreds of kilometers per second. Warm, somewhere in between. Yeah. Okay, maybe we'll leave it there, and any other questions you can come up at the end and ask me. Thank you.